everybody. Welcome to this seminar. I'm very honored to introduce you our guest speaker, Professor Jordi Arbiol. He is ICREA research professor and group leader at the Catalan Institute of Nanoscience and Nanotechnology in Barcelona, the ICN2. He is a former president of the Spanish Microscopy Society and currently executive board member of the International Federation of Microscopy Societies. He is one of the founding members of DREAMS, an international network to perform PM experiments worldwide, recently appointed as associate editor to Nanoletter. During his career, Professor Arbiol received many recognition and awards, including the EU40 prize at EMRS in 2014. At ICN2, he is scientific supervisor of the electron microscopy area and the scientific coordinator of the Joint Electron Microscopy Center at ALBA, which is a state-of-the-art new microscopy facility, which will be dedicated to the investigation of nanostructured materials, both in situ and ex situ. During my career, I'm very happy that and very lucky that I had the chance to work many years with him, and I'm happy to announce that recently the Department of Physics and Astronomy signed an agreement with the ICN2 and Professor Jordi Arbiol to continue collaborating and exchanging students, researchers, and above all, experiences. Well, Jordi Arbiol is a physicist working in the field of electron microscopy applied to nanostructures, with application mainly on energy and quantum field. And in particular today, as you can see from the title, quantum nanostructure at the atomic scale, he will tell us about his leading activities in this field, describing the evolution of nanostructured devices, which are the building blocks for quantum computing, which will completely change our life. Jordi, please, the floor is yours.
Thank you very much, Chiara. And thank you, all of you, also Salvo, for letting me stay here. And an honor to be in front of Francesco, because many years ago, in 2014, I was still young. And he gave me the award for the EU40 in the EMRS, so really honored. So what to talk about today? So we are a group of electron microscopy, as Chiara said, and we work on many different topics. So you see that, for example, we work with, let's say, nanowires for quantum applications, photonics, electronics, etc. Also in nanostructures for energy and catalysis, oxides and ceramics, biomaterials for biology applications. That we're supposed to show this Majorana effect. So this is a long story, which started like 20 years ago, so a long time. But you will see how this follows and it's evolving. So it's a talk that can be named, as I said today, quantum nanostructures at atomic scale, but it's also the story of nanowires. Nanowires applied to photonics, electronics, and nowadays supposed to be for quantum application. Okay? So the main idea here, starting from history back 20 years ago, we were starting. This is the typical BLS growth, vapor-liquid-solid. So this is a way to grow nanowires out of a substrate, and the way to create this kind of vertical nanostructure. You can create nanowires, tripods, tetrapods, this type of nanocells, as we called them in the past. So there are many things you can do, playing around with the growth conditions. And I will try to show you a trick in order to identify how you can easily think how to create every one of these structures and how you can apply this type of morphologies for many different applications. So the first idea came out with this student along the way. It was year 2008-9. When I moved to the Institute of Material Science in the UAB campus in Barcelona. And we started working with nanowires with a really extremely good researcher, Ana Foncuberta y Morral, now she has been selected president of the EPFL, so she's a big boss right now. But then we were like young students, not students, but postdocs, okay? So at that time, she was growing many different types of materials, and we were mainly gallium arsenides, and we were collaborating with many other groups working in 3,5 materials and also 2,6 materials. So you can see here the big amount of different, this is the nanowire, and this is how they look at the atomic scale. So we were dealing with many different types of materials. But what Maria did and what we were searching is that every time we were looking at the atomic structure of these nanowires, we could always see that there was a kind of polarity there. A polarity meaning that every one of these structures, either if it is cubic or hexagonal, at the end they grow showing the anion always on top. And this means that even gallium nitrate is showing the nitrogen on top, gallium phosphide, the phosphorus on top, arsenic on top, antimonium on top. And the same was happening here, like tellurium, selenium, and sulfur, and for many different types of materials. And this was what we called this directional or unidirectional polar growth. So if you think about that, these nanowires were following a kind of growth conditions which were giving the, let's say, the fastest growth. So whenever you wanted to grow these nanowires really fast, without defects, etc., you were obtaining these polarities. If you wanted to reverse the polarity, then you had to change the growth conditions a lot, and then the growth was really slow. You could also grow them in another polarity, but then the growth was slow and the yield was not so good. Okay, so by growing them on the good conditions, let's say these good conditions, the polarity was always showing the anion on top. But there was one exception, and this is the zinc oxide. Maybe because this is the only oxide in all the list, but the zinc oxide was always showing the cation on top. Zinc was always on top. Okay, so by following this rule, we had, as I said, for 20 years working on how these materials work, and at the end we could realize by doing many theoretical simulations why these materials were showing the dumbbell. The dumbbell is this pair of atoms, the cation plus the anion, and why they were showing on one side the cation on top and on the other side the anion on top. So this is a long story. I just wanted to show you this. But following these simple rules that in every fast growth condition, what you get is always the anion on top, you can realize that if you want to grow on top of unpolar materials like silicon, in the case of silicon or germanium, all the atoms are silicon, so there's no polarity. So that means that the first seed that you are nucleating on top of the substrate can be either terminated in the cation or the anion, it doesn't matter. So at the end, you just nucleate, depending on the growth conditions, you will get one or another. But then let's take this typical octahedron. This is showing all the possible 1-1-1 facets that you can get in this cubic structure of the gallium arsenide, okay? The red ones are the ones terminated in gallium, the cation polarity. And the yellow ones are the ones that are showing the anion polarity, terminated in arsenic. So if the first nucleation seed that is falling on top of the silicon is terminated in a cation facet, in an arsenic facet, an ion, then you will be able to grow a vertical nanowire. That is easy because we will have the anion surface just liberated and you can grow on top. But if we inverse the seed that is growing in the first time, you will not be able to grow a vertical nanowire because this facet on top will be terminated in a cation and then it will be forbidden. So instead of that, what you can see is that there are 3 other facets available, the ones terminated in the, let's say, yellow for the anion, that will be possible to grow this material. In this case, what you will get is a tripod, because instead of growing a vertical nanowire, you will have 3 different facets available for the growth. And this is what we tried to investigate with all these different facets. So imagine that your first nucleation seed, if the video starts, it's not terminated in the anion, but we reverse the polarity. Pretty slow this, it should be a little bit faster. But imagine that the blue one on top is the cation. So what we will have is 3 other available facets, and then the branches will grow along the anion, creating this really nice tripod that you can see here. So this is the structure of the tripod. But what happens if we want to create a tetrapod? So instead of having a perfect, let's say, octahedra, what we can do is nucleating a faceted or truncated octahedron. In this case, if we truncate the octahedron on the 110, or if we do it on the 112, we will get different possibilities for the facets. Then we can create a second nucleation event, creating another octahedron with 3 more available facets on the anion sides, the same here. And then depending on the different angles that you get for the different truncation, you can get this type of tetrapods or this other type of tetrapod, where these legs are just falling on top of the substrate. So it's quite easy. Just think about the anion polarity, and then you can create all these different facets. The same is here. When you think about quantum materials, you want one of these semiconductor materials that have maybe a small bandgap, but also a really high mobility. And when you think about a high mobility, you can think about indium arsenide, but the best material is maybe indium antimonide, or one of the best, for the mobility reasons. But it's really difficult to grow indium antimonide nanowires, at least by using this DLS technology. So what you need to do is growing first an indium arsenide nanowire, and then on top of that, you can grow the indium antimonide, okay? But then from time to time, we realized that instead of nanowires, we were growing indium antimonide nanocells, which are completely different. And we could not understand why in one case you could have this 2D layer, and in the other case you had a perfect nanowire. So let's see at the atomic scale what is going on there in order to understand the structure and why the structure is leading to a different morphology. So in the first case, you have the indium arsenide nanowire. It has a kind of hexagonal cross-section. Every one of the facets here is a 110 facet. This is an unpolar facet. So it's not allowed to grow like on the width. So this, you can change the growth conditions and then make the nanowire wider. But in this case, if you want to grow in the axial way, you can use growth conditions in which the unpolar surface is not growing anymore, okay? But you see that the indium arsenide is growing on top, but also having exactly the same facets. These are the 110 facets that do not allow the nanowire to grow on the side. So here there are many mechanisms. Indium arsenide is an hexagonal structure. You can see a kind of zigzag of the atomic layers. These are the 001 layers that are having this zigzag structure, AB, AB, AB. And then this is the cubic structure of the indium antimonide, which is an ABC, ABC, ABC piling of the atoms. So the stacking is quite different in one and the other. But what you can see here is that all the strain is released at the first 5 nanometers of the nanowire, and then everything grows relaxed. So this is a really nice way to grow materials with high purity, because if you grow a nanowire after the first, let's say, nanometers, when everything is super strained, you have a perfect growth with the material fully relaxed. What you can see here in this picture, this is a rotation map. You see that on both sides at the interface, on both sides there is a plus minus 8 degrees rotation of the planes. And this means that there is a kind of plastical relaxation. So the material tries to adapt. One way to adapt is with elastic relaxation. And here you can see how there are misfit dislocations, one here and another here. But also there is a competing force of relaxation methods competing the plastic relaxation with elastic relaxation. Okay, there is a combination of relaxation mechanisms until the material just grows without any other defect. So this is what happens with the normal nanowire. But then let's investigate what happens in the nanocell. Why is so different if we grow in the same batch and exactly with the same conditions? What we found is that in every single nanocell, exactly at the interface, we could find a twin boundary. So there is a kind of nucleation misfit here in which a twin dislocation is appearing. And what this dislocation was creating, it's a breaking of the symmetry here. So this 110 facet was broken, and instead of that, you change with this twin boundary, and instead of having a perfectly unpolar surface, here you have a perfect polar surface and exactly terminated in the anion. So what this was doing is breaking the symmetry and allowing the material to grow to this side as well. And this was the reason why you could create these really nice nanocells. So what we do is analyzing the catalyst seed, that is the one promoting the growth. And after the growth, of course, everything is crystalline because you cool down the material and then it gets crystalline. The crystallinity is so perfect that the gold and indium or gold indium composite that you have here, it's perfectly attached to the indium antimonide. You can see here a perfect epitaxy. You can see all the atoms there, the gold atoms surrounded by 2 atoms of indium. This is perfect, but this is happening when you cool down the material. But during the growth, all this is completely liquid. So the droplet, the gold, is completely liquid during the growth. So what is going on during the growth? And I will try to show you with this model. So at the beginning, this is the final nanocell, but at the beginning, what you have is the indium arsenide, and then this is the indium and gold droplet that you have on top. This is the cross-section of the nanowire, perfectly hexagonal, with 6 110 facets that are unpolar. And then suddenly, when you are starting to add the antimonium, this droplet grows. And when it grows, from time to time, this droplet tends to fall to one of the sides. And when it falls, it creates this twin boundary that breaks the symmetry and allows the material to grow to this other surface, which is not unpolar anymore, because it has this axial polarity with the cation, with the anion on top. So you can grow to the side and continue growing until you get rid of the small indium gold droplet, which gets smaller, smaller, and smaller. Okay, so this is the growth mechanism of this nanocell. Of course, we then analyze these nanocells, and you had a perfect ballistic regime, so meaning that quantum properties were arising from this material because it was perfect. At the end, you had only one twin boundary, which was on the side of the material. And if you avoid that side, the rest of the material has no strain. So it's growing without defects and perfectly attached to the substrate. So you can remove it and just contact it. And then let's go for Majorana. Okay. So what do we need in order to create Majorana bound states out of a semiconductor? Okay, let's see. So this is the technology that, for example, Microsoft, a company that you all know, because some of you have computers that belong or they are from Microsoft or at least some software. So these guys, and we've been working with them for the last 7, 8 years, and they were trying to develop a technology in order to use the Majorana fermions as quantum states for quantum computing. So there is a strong branch in Microsoft and all the other companies, Google as well, and Samsung, and all of them have a branch for quantum technologies. And what they are trying to develop is the quantum computer of the future. You know, for example, IBM, they already have several chips with, now I think it's 2000, between 1000 and 2000 quantum bits in a chip. So they are growing and growing. But the idea with this technology is that it should be, because they didn't reach it yet, but it should be fully scalable. So that means that once you get the first quantum bit, you can scale it up to billions of them. And that was the idea here. Because if you use these Majorana bound states, they are topologically protected. So noise is not affecting them, and you could really create this type of, let's say, structures and networks having all these quantum bits all interconnected. And that was the idea, and you will see how this should work and how it failed. So this is the complete story, okay? So the quantum technology is based on the Majorana bound states. First of all, what you need is one-dimensional spinless nanowire. And for this, what will you need? You need a one-dimensional superconductor. I was talking about a semiconductor, okay? But here appears the word superconductor. So you need a strong spin-orbit coupling. That's another of the things you need. Low effective mass, high mobility. When I'm talking about high mobility, you think about what I said before, indium antimonide, indium arsenide. So that is the semiconductor part. You need a low positive-particle poisoning rates, gateable system. This is very important. How to gate all these millions and millions of, let's say, quantum bits. You have many quantum bits. You need to connect them And you need to create a single chip with all these interconnected networks. And that is the most tricky part. And finally, you need to withstand with high magnetic fields. Or let's see, I will show you about the intrinsic splitting, but by magnetic coupling. But the idea is that you should grow a nanowire. This is a nanowire with a semiconductor, a high mobility semiconductor. And then on top, you try to grow a superconductor. Okay? And this is the 1D superconductor because you will grow it on top of a nanowire. That's the main idea. Let's see. And then what you will try to create is this type of networks in which, okay, we should have here these Majorana fermions. So let's see the different technologies or different approaches that you can get in order to get the type of morphology I was showing you before. One is this type of two-dimensional electron gas or two-dimensional hole gas, depending if you use 3,5 material or silicon or germanium, depending if you use the holes or in the case of silicon, if you use the electron spin. And then this is a type of material. I will not talk about this today because there are too many things that would extend much more. Then there is another way to do it. Doesn't want to work. Okay. It happened before. So no, before starting, it happened, but then it suddenly worked again. So hope it works. Not the, no, because it didn't work and then suddenly worked again. So that's, I don't know, maybe it's my computer. So this is for the two-dimensional electron gas, hole and gas. Then there is this option with VLS, vapor-liquid-solid nanowires, the ones that are standing up. So this is the first technology I was telling you about. And then the last one, which seems to be the one that is preferred for technological reasons, is the one of selected area growth, in which you can grow the nanowires directly on top of the substrate and create directly these interconnected networks. Okay, that would be the easiest one, the easiest solution. So let's see. So in all this, we have been working a lot with these different types of materials. And at the end, what I told you, it's this selected area growth in which you prepare some trenches on top of the substrate, and you only grow the material inside the trench. So this is the semiconductor. And once the semiconductor is grown, you can couple it with the superconductor only on one or two of the facets. Like here, this can be aluminum, for example. You can use aluminum as superconductor. And then here you have finally the Majorana network with a lot of interconnected quantum bits. Okay, so let's see what happened, because this ideally for theoreticians that should work. And then let's go for experimentalists. We are the bad guys here, the electron microscopists. So okay, we have the indium antimonide or indium arsenide nanowire. In this case, this is a cross section. So we cut with a FIP, focus ion beam. You can cut a slice of this and then check at the slice. And then this is indium arsenide, super nice. This is the atomic structure. You can see all the atoms here, super nice, super beautiful. And then you grow aluminum on top, covering some of the facets of the indium arsenide. Oh, aluminum. Aluminum is a metal, it's a metal. But if you work at the millikelvin range, it can work as a superconductor. And it works. It's really nice. It works as a superconductor. But the problem is that we have many epitaxial problems here. So whenever you grow on top, this can be cubic or hexagonal, but at the end, you can attach perfectly the aluminum, but there are a lot of misfit dislocations at the interface. That is one point. Then you see that all the material grows perfectly, let's say, relaxed, which is okay. The main problem is that from time to time, you create these twin boundaries. So the material tends to rotate 180 degrees, and you have many different boundaries. So maybe this is not super good for the idealistic properties you need. So it's not the mismatch at the end, which is 27%, which is a lot, because the material, it's all relaxed at the interface. A lot of misfit dislocations are relaxed in the material, and then it grows quite well. But the problem is maybe the formation of all these twin bonds. But there is more. Then with these materials, you need to use super high magnetic fields. A way to get rid of this is by using a ferromagnetic insulator between the semiconductor and the superconductor. And this is a way to keep the spin degeneracy, but not using these large external magnetic fields, okay? Because then you could weaken the supercomputing pairing. But the thing is, okay, we were thinking about europium sulfide, which is a nice ferromagnetic insulator, but then you take into account the indium arsenide. It looks like this hexagonal shape. This is the cross section. And then let me see if I can show you. Okay, can you see this is the beautiful structure of the indium arsenide? It's an hexagonal structure, super beautiful. But then on top, you see that there are like a kind of grain boundaries, and they are like flexing or rotating slightly, so they are not perfectly adapted. So the point is that the answer is here. If you want to adapt these two materials, what you need to do is getting exactly the same lattice parameter. But when you are nucleating the europium sulfide, it is nucleated in different points at the same time. And when these crystals grow, they try to adapt to the material beneath, and they do it in the best way they know. So they need to turn or rotate a little bit in order to make all the planes coincident with the ones of the indium arsenide. And this is okay. But then when two of these different boundaries are merging, the problem is that some of them goes to the left, some of them go to the right. And these grain boundaries are really messy for the material. But then what we realized is that, okay, we have some corners here at the edges of the nanowire where the facet is not this is a facet that it's 1, 1 minus 2, 0 facet. But then if we go to the 1, 1, 0, 0 facet here, we see that the atomic planes of the europium sulfide are perfectly aligned and vertical compared to the ones of the indium arsenide. So if instead of growing these 1, 1 minus 2, 0 facets, we tend to grow bigger edges instead of this, we will be able to adapt the material in a better way. And this is what we did in this other nanowire, preparing these facets or these edges a little bit longer in order to have a better adaptation of the atomic planes. So there is a way to play around. Changing completely the growth conditions, you can switch from these facets to these other facets. It's possible. But then the growth is not so quick, and then there are many other problems, okay? But there's always a solution to go through. And then the idea, we use aluminum. Aluminum is a good semiconductor, but there are many others. Why don't we use other superconductors? In the case of tin, it's a very interesting, really superconductor, because we don't need to work at the millikelvin regime. Maybe at the Kelvin regime is a problem, which is really low still, but it's not millikelvin, it's few Kelvin, 3.7, okay? So the idea here was using this beta tin, the beta phase of the tin, in order to be attached to the indium antimonide arsenide or indium arsenide. But the problem is that there is another phase of tin which is cubic, and it has exactly the same lattice parameter of the indium antimonide. So come on, this is again a problem, because when you try to attach tin on top of the indium antimonide, what you get is a perfect layer of alpha tin, not beta tin, which is the one we want. So at the end, what we did is, if you grow this lattice a little bit more and you switch the temperature, once you get the alpha tin, you can grow you create a kind of twin boundaries, which you can see here. And then on these twin boundaries, you can switch a little bit the temperature and nucleate these other grains of the beta grains of beta tin. And then in this case, you can grow this beta tin a little bit better. So you finally get the superconductor phase of tin. It's possible also, instead of indium arsenide, instead of indium antimonide, to use indium arsenide in an hexagonal structure, and then the first alpha tin, it's not attaching, because then the cubic phase cannot attach to the hexagonal one, and then the only one that you get is the beta tin. But these are like ways that you need to think and change temperatures, change the pressure inside the chamber, etc., in order to promote one or the other one. But only the beta one is the one that we need for this. So finally, does it work? Are they really Majorana fermions? So you have seen in literature, or at least, I don't know, you are in the Majorana department, Majorana, so I'm sure you have read many natures and science papers dealing with this 10 or 12 years ago. There were many groups claiming about the Majorana fermions in this type of semiconductor nanowires. And at the end, many of these papers were rejected, not rejected, but retracted, because they could not really demonstrate. So they could find qubits, and they could find, let's say, quantum states, which work, but not Majorana. So the way, not us, I mean, we are in this paper, but because we were analyzing the nanowires, but the guys that did all the theory and really comparing by tunneling and Coulomb blockade spectroscopies, both together, they could demonstrate without no doubt that they were not Majorana fermions. Because if you only use one of the techniques, you cannot be sure 100%. You can claim they are Majorana, because what you see, it's compatible with the Majorana fermions. But if you use both at the same time, you realize that they are not really Majorana. Okay, so at the moment, nobody can claim with the technology we have that these nanowires are really showing Majorana fermions. And the reason, again, is what I showed you before. There are many in the superconductor material, at least from the structural point of view, you have many twin boundaries and imperfections that do not let you to have the perfect structure that you need for this such type of quantum properties. Okay, so this is like a end of story for this, which I hope people will still work on that, because there is a lot of room to improve the materials, and I'm pretty sure that finally they will find the Majorana fermions. So another problem, and this is the biggest one, even if we have the Majorana fermions, or even if we can use the quantum, let's say, quantum particles that really exist on those materials, the second problem is how to gate these nanowires. So I showed you that they are growing vertically, but then we need to cut them one by one and make this kind of circuits. So this is useful for one of them. So you can create really beautiful devices with one nanowire. But imagine if you need to create a computer with billions of these or millions of these nanowires, and all of them have to be like connected one by one. It would be impossible. So at the end, this technology, it's not really affordable. Then many groups have tried to grow the nanowires like this in a kind of interconnected way, but it's not really 100% perfect. And for this type of technology, you really need perfect structure. That every single nanowire has to be interconnected in the same way at the atom side. So you see that this is a kind of promising way to do it, but it's not still good. So this is why many groups have moved to the growth of these, not vertical, but planar nanowires. So if you can grow the nanowires directly on the substrate, then they can be more easily, all of them interconnected. And that's the idea. But then another problem starts here, because I was showing you at the beginning that if you grow vertical nanowires, all the strain, all the defects are at the interface with the substrate. And then the nanowire grows perfectly without the strain and without defects. But now we have a huge substrate interaction here. So all the nanowire is growing on top of a substrate, and there is a lot of strain in between both materials. So this is something that we need to understand and get rid of this. So these are not the perfect nanowires I will show you later, but it's just an example that makes me explain you which are the difficulties and the things that are going on when you have different things growing on top of a substrate. And the thing is, imagine we have a core shell nanowire in which this is the substrate. This is a cross section, so this is only a slice of the nanowire. Imagine that this is a kind of cylindrical core in the middle, and you try to grow a shell on top of that. You can see that, okay, there is no strain, so everything is growing homogeneously on top. So this is a map of the dilatation of the interatomic distances, though it's quite homogeneous. And what you can see here is that there is it's quite homogeneous for all of them. But when you compare the rotation, you see that the atomic plates on both sides get rotated. You see in blue and green, these are different angles. So it means that the atomic planes, which should be like planar here, try to deform in order to adapt to the shape of the cylindrical core in the middle. And this is what you see here. A lot of misfit dislocations on the side, and then there's no strain almost here, but a strong change. And this is a rotation of plus minus 2 degrees. It's just maybe not a lot, but you will see that it is. So this is if you get a profile here, you see that this is a minus 2 degrees, this is a plus 2 degrees when you cross from one side to the other. So the atomic plates are just bending on both sides, okay? Instead, if you use a planar core, the shell that is growing on top is growing in a planar way. In this case, there is no rotation, which is good. There are some misfit dislocations maybe on the sides, but then most of the shell is growing without any rotation, which is much better. Then if you compare different types of morphologies in the core, you see that there is a different way of rotating on both sides. And the worst is for this case, which is the perfectly cylindrical one. But again, let's think about the tangles I told you before. We have polar structures. And these polar structures mean that you have a cation and you have an anion. But if you rotate them, what you get is a polar interface. And what this is giving you, if you simulate this, so this is a simulation of what is going on. This is the experimental shape. This is the experimental image of the rotation. This is the simulated one. And then you can calculate what is going on in the electric field. And what you see is that there is a strong field, electric field here at the interface due to this rotation and the polarity of these atoms that are bending exactly there. Okay, you can see it here. This is the electrostatic field that is appearing in the middle, exactly. And there is also a bending in the bands, for the valence bands a little, for the conduction bands a little bit. So this is affecting the material. But what is worse, it has to come now. So you can measure with the new microscopes we have, you can measure the band gap at the sub-nanometer scale. So every pixel here in this picture is a measurement of the band gap in this nanowire. So every pixel is around 0.9 nanometers. So we are at the sub-nanometer, let's say, scale. And you can see how the band gap is almost homogeneous in the core, is almost homogeneous in the shell, and the values are close to the theoretical ones. But what we could do is comparing and determining which part is indirect band gap and which part is direct band gap, depending on the slope of this in the electron energy loss spectroscopy spectra. And what we could see is what you can see here. Exactly at the interface, there is a strong strain. You can see this bright contrast here, means that there is a lot of strain exactly at the interface. And what this is doing is a change in the band gap from direct to indirect. So you see that the substrate is it's sapphire. So in sapphire, you have a strong indirect band gap, but also at the interface in 2-3 nanometers, you have this change from direct to indirect band gap, and also a small decrease in the total value of the energy band gap. And this can be detrimental for your material. So this is something to take into account if you really want to use these materials for, I don't know, photonic use or electronic use, okay? So going again to the selected area growth, in this case, these are perfectly controlled growth nanowires. And you can see that you can grow the nanowires on every single direction. So this is a 001 substrate. And then we tried to grow the nanowires on every single direction, just changing 3 degrees rotation for every one of them, and just analyzing how they grow at different directions. And you can see here that depending on the direction, these are cross sections taken at the 1, 0, 0, 1, minus 1, 0, and 1, 1, 0. And you see that the morphology and faceting of every one of the wires is completely different. So the material tries to minimize the surface energy, and depending on the direction it's taking, different facets are arising. So that's another important point to get into account, because depending on the slope of these sites, you will grow better or not the aluminum on top if you want to grow the superconductor. And then another thing is that, again, there is an elastic relaxation on both sides. You see that the material, of course, is bending because it tries to adapt to the shape of the nanowire. So you see that there is a strong elastic relaxation, but also strong plastic relaxation with the formation of misfit dislocations. But what is good is that the outer layer, which is the one that we will use for high mobility, this is the pure indium arsenide. Here, there is no strain at all because everything is relaxed at the interface, and here at the interface with the substrate. So it's good. At the end, you can create really nice materials or semiconductor material just on top and in one dimension because they are fully axial on top of the substrate. And then you can, of course, measure the different quantum properties, and you get that you have a quite decent ballistic regime for the mobility and the conductivity, which is also good. And it's demonstrating that, yeah, this type of materials can work as quantum materials for quantum purposes. So at the end, I hope you like the story. I have one more thing to show you if you want. If not, we can finish here. But I hope you like the story of these nanowires or the evolution. I call it revolution because they started with vertical nanowires. Now they are growing directly on top of the surface. There is a lot of room of improvement, and things are going on. Many publications on the field and many groups around the world and companies working on this type of technologies. So this is what I told you about these other materials, but I will not talk about it today. But I came to visit Salvo and Chiara, and then, yeah, you are interested in this. So just for you, okay. So now I showed you how the purity of the materials is very important for physical application. But then what about the chemist? The chemist, okay, the purity is not so important. Let's see. So if you want to work on catalysis, sometimes the purest material is not the best one. Maybe. And I will try to show you that there are ways to destroy your material and make it a bit better. Okay? So imagine you want to work on catalysis for hydrogen evolution. This is splitting the water molecule to get the hydrogen out of it and create green hydrogen. If you activate everything with a solar cell, for example, and then one promising material is platinum. Platinum is very expensive, so if we work with platinum nanoparticles or platinum in bulk, is too expensive. So the ideal way to work with platinum or noble metals would be to have a perfect one-dimensional layer of platinum. That could be the perfect thing. Because in catalysis, what we want is that all the surface reactions are happening, of course, on the surface. So everything we have beneath the surface is useless because it's material that you are losing, material that is not active. So in this case, if you have a perfect 2D layer of platinum, you are not wasting much platinum, but all the platinum there will be working in the catalysis reaction. So there is a way to prepare platinum biselenide, which is a nice material. It's a kind of sandwich. You have selenium atoms, platinum atoms, and then again a selenium copper layer. So it's a kind of 3-fold layer. It's similar to the molybdenum disulfide. So you have sulfur, molybdenum, and sulfur. So here you have selenium, platinum, and selenium. What a nice idea. You have the 2D layer of platinum. Then you try to make it work, and it doesn't. It doesn't work. So it works a little bit, but not much. So it's not a good catalyst. But then it came out the idea of these collaborators in which why don't we apply a plasma, argon plasma, and we try to destroy the surface a little bit, creating selenium vacancies. What happened then? If you create selenium vacancies on the top, what you are doing is extracting some selenium atoms and then leaving the platinum that is beneath to be free. Then you have dangling bonds there, which are really avid for the water molecules. And this will be working. So the idea is trying to amorphize your material in order to get rid of 30–40% of the selenium atoms on top to make the platinum beneath to really be active and work. And let's see if this works. So applying the plasma at different times, you can get from the perfect material until you get this perfectly amorphous material. How do we see that? Every single dot here is a platinum atom. And if you can see, they are not distributed in the structure that they should be. So the perfect structure looks like this. This is the platinum distellanite. You can see perfectly all ordered atoms of platinum. But in the case of the amorphous layer, after the plasma etching, you see that every atom is in a random distribution. And you can see here that the FFT, which gives you the structure, is completely amorphous. You cannot see spots of a decent structure. So another thing you can see here is that there are no clusters. So every single atom, it's not attached to another atom of platinum. And you can see it here. So the crystalline, if you get the XRD, no, this is Raman. So in Raman, you have to multiply by 10 in order to get the structure. So there is almost no structure compared to the bare material before the etching. But here, if you get the XPS, you realize that there's no platinum zero. And that's the point. This is the key point. Because platinum zero means that you have metallic bonding. And here there is almost no metallic bonding, meaning that there is no clustering. So every single atom of platinum is still attached to the selenium beneath, but it's free to move. And it's not being collected as a platinum zero, as a metal. So these are these molecular dynamic simulations for different timing. And what you see is the displacement of the platinum atom. At the beginning, all the platinum atoms are in the correct position. And then when you start the plasma, at the end, they are randomly distributed. They are moved from the perfect position. Okay, I will be super quick. Then you compare here. This is the displacement of the platinum after the plasma etching, and then, of course, you increase the number of vacancies of selenium. So the stoichiometry is increasing the number of vacancies. So for this stoichiometry, you have the highest number of vacancies. And what you can see, this is a cross section. In this case, this is not the atomic layer. What we did is grow a thicker layer because otherwise we cannot prepare it by fit. But we were attacking in order to see how was reacting to the plasma, the top layer. And you can see that in the layers inside, the distance is constant, but on the top layer, this is the random distribution. Every single atom is in a different position. And at the end, if you compare with the Tafel slope and everything, you see that the best numbers, the minimum numbers for the Tafel slope, for example, and the offset potential, the minimum ones, are for the ones that are perfectly amorphized. And the comparison with a perfect platinum, it's exactly the same. It works as a perfect platinum foil. Okay, so without expending so much platinum, because at the end it's a single layer. Okay, and here you should see the bubbles, because this is, hopefully you can see the bubbles. I will just click once. Okay, yes, here you see the bubbles. Here you see the bubbles. So this is the hydrogen being created out of this. So it seems it worked, and it has a really high stability. So after 100 hours, this is still stable. But there is a trick. There's a trick. Because the material gets degraded. So at the end, what you get is that you are losing platinum, you are losing more selenium. So you need to re-selenitize the material all the time. But there is a trick. You can do it, and then everything is super stable if you do it. And if you compare the material after the treatment, it works like this. The material without treatment, the burst substrate, it almost has no reaction. So that's the idea I wanted to show you. And then, yes, this works for all these noble metals. So you can create platinum diselenide, palladium, iridium, osmium diselenide, etc. It works for all of them. But if instead of noble metals, you use molybdenum, tungsten, rhenium, and so on, in this case, they are not so stable because they get oxidized quite easily after 30 days. You see that the material is decomposed. But in the case of the noble metals, they are still working after 30 days, okay? In nice conditions. They are still working. So this is the demo that all these different materials, after being amorphized, they are really working and have a really good performance. So my last slide, it's just to show you, this is the JEMCA, the Joint Electron Microscopy Center at the ALBA synchrotron. And here is where Chiara, when she's visiting us, it's coming and using this microscope that can show you these beautiful pictures of the structures and atoms that I was showing you today. And the nice thing is that it's in the ALBA synchrotron. So we have now one for material science, one for cryo and biology, but another one for in situ is coming at the beginning of next year. And we hope to be able to do catalysis inside the TM and see the reactions in situ with all the atomic changes. So just to thank all collaborators, I will not name them all because there are so many, and also from different microscopy facilities, theoreticians in microscopy that were helping a lot on all this, and of course all the projects and everything, and of course all the group and the guys that are doing all this work. Thank you.